This video is a continuation of the lecture Interval Estimation of the Mean. When we collect enough random samples for our study, we are aware that our sample mean is part of a normal distribution. Okay, so we have our sample mean as stated by the central limit theorem. And the mean here of our sample mean is the population mean. But in order to do an interval estimation of the population mean, so in order to do an interval estimation, we need to work first with this normal distribution by standardizing it. So we need to standardize this. But since we do not have information on the population standard deviation to do a z-score, okay, so take note, the z-score needs the population standard deviation. We instead use the sample standard deviation to perform t-scoring. So we instead use t-scores. The t-scores or t-statistics will then follow a distribution that looks like a standard normal distribution, but not quite, which we call the t-distribution. So when we standardize this by t-scoring, we end up with a distribution that looks like a normal distribution, but it's actually the t-distribution. So take note that there are many types of t-distributions, depending on your degree of freedom. That's why we have a t sub d, which is based, of course, on your number of samples. So remember, the degree of freedom is n minus 1. So just like the standard normal distribution, the total area under the t-distribution, so this is now our t-distribution, is 1 or 100%. So everything inside this t-distribution is 100% or 1. Now, we will now assume a value we call alpha. Okay, so alpha. So alpha will be a small portion of the area under the t-distribution. Say we can give it a value of 0.05 or 5%. If we divide this alpha by 2, then we have a notation alpha over 2. In the case of alpha being 5%, alpha over 2 will be 0.025 or 2.5%. Okay, now, we can see in this illustration that alpha over 2 are found here at the tails of our t-distribution. Okay, so let us dissect this particular expression here. Okay, so it says the probability that a t-distribution, or the probability that a t-value will fall between alpha over 2 percentile of a t-distribution with n minus 1 degree of freedom and 1 minus alpha over 2 percentile of a t-distribution with n minus 1 degree of freedom is 1 minus alpha percent. So if we consider our alpha back here as 0.05 and we try to rewrite this expression, then we'll have something like this. The probability that our t-value will be greater than a t-value of a t-distribution with n minus 1 degree of freedom and What's our alpha over 2? Our alpha over 2 is 2.5 or 0.025 and lesser than a t value that's part of a t distribution with n minus 1 degree of freedom, and on the 1 minus 0.025 percentile will be equal to 1 minus 0.05%. Okay? So if we simplify this one, we'll come up with PR, then you have Tn minus 1, comma 0.025, and then less than sign, our t value, and then another less than sign, and then Tn minus 1 degree of freedom, comma, what's 1 minus 0.025? So this is 0.975, close parenthesis, and this is equal to 0.95. Okay, or 95%. So that is this remaining area here in the middle. So if we illustrate that here, this one is your 0.95, and then this alpha over 2 here, this portion is your 0.025, and then this portion here will be your 0.975. Okay, so everything here in the middle is 95%. And these boundaries are 0.025 and 0.975 respectively. So it's important to be familiar with what we are doing here, because the t distribution, as you can see here, will be used. It's the distribution that we will be using to do an interval estimation of the population mean. So, as I was saying, in doing an interval estimation of the population mean, using the t distribution of sample means, we use this notation. So this looks similar to the previous one. But this time, we include the sample mean, the sample standard deviation, and number of samples in the mix. So instead of just a t-value, we now have the population mean that we are trying to predict its location. Okay? And it's greater than this value, which includes sample mean, and then the sample standard deviation, and then the number of samples. And it's lesser than this value, which also includes the sample mean, same sample mean as we see here, standard deviation, same as the one here, and the number of samples, same as the one here. The only difference is here we need to subtract on the left. On the right side, we add. And the probability of getting this interval is equal to 1 minus alpha %. So, in fact, this resulting interval is called the confidence interval for the mean, or in short, CI of the normal distribution. And in order to make this shorter, this notation, we can write it this way. So we just combine the plus and minus signs in this portion. Okay? So if we just observe this particular expression, we will be able to get a confidence interval or an interval estimate, as I am drawing the line here. This is the interval for our population mean here in the middle. So let's try an example on how we can work with this expression. Okay, so here we are asked to compute a 95% confidence interval for the mean birth weight based on the first sample of size 10. So we will base it on just this first sample. We will make a 95% confidence interval for the mean birth weight. So again, we go back to this expression. So this one is based from your t distribution. And what we need to do is simply replace the correct variables with the correct values, and then we will be able to get the confidence interval. Okay? So, first and foremost, just to be clear, let me remind you that this whole quantity here should be done first. The ones I'm putting inside the bracket should be done first before you subtract or add with the sample mean. Okay, so let's replace these variables with the values. Okay, so first, what is the sample mean of our first sampling here? It's 116.9. Okay, and then we subtract, okay, t sub n minus 1, and then 1 minus alpha over 2 percentile. So what is this t sub n minus 1? Our number of samples here is 10. So therefore, this is a t distribution. Let me put that in a parenthesis. Minus a t distribution with a 9 degree of freedom. And what will be our percentile? What's 1 minus alpha over 2? Now, because we are being asked for a 95% confidence interval, the remaining 5% will be our alpha, or 0.05. So, this 1 minus alpha over 2 is actually a 1 minus, what's alpha over 2? What's 0.05 over 2? Our alpha over 2 will be 0.025. So this is 1 minus 0.025. Okay? And then we need to multiply this with a standard deviation, as we see here, which is 21.70. And then after we divide the product by the square root of the number of samples, and that's square root of 10. Okay, so that's on the other side. That's on the left side. Now let's go to the right side. I'm just going to write it here at the bottom. Okay, so for this portion now, you now have still 116.90, but this time we are going to add. Okay, we're going to add it to the value of t with 9 degree of freedom and 1 minus 0.025 percentile times standard deviation 21.7 divided by square root of the number of samples. So we now have replaced most of our variables with the actual values. Okay? But before that, we have to reconcile what this one is. What is that 1 minus 0.025? Okay? That value is 0.975. 0.975. Okay, so now let's continue with this. Okay, so this is next one. So we have 116.9 minus. So you now need to go to the T distribution table. I think that's in table 5 at the appendix of the book. What is the equivalent value of the T distribution with 9 degree of freedom and 0.975 percentile? Okay, if you go back at the back of the book, at the appendix, you will find out that that's actually 2.262. Okay, so that's the value of that T distribution. And then we multiply that with the standard deviation, 21.70. And then we divide with the square root of the number of samples. That's our left side. Okay, and for our right side, we have 116.90 plus, so the same values, 2.262 times 21.7 divided by square root of 10. Okay, so if we simplify these, we'll now arrive at 116.90 minus, okay, you multiply these first, and the answer there will be more or less 49.085, and we divide that by the square root of 10, which is 3.16, okay, and then comma. On the right side, we have 116.90. Instead of minus, we have a plus. And then the same numbers, 49.085 over 3.16. So we are now starting to see the interval. So this is just 116.90 minus 15.53, and then comma. On the right side, 116.90 plus 15.53. Our 95% confidence interval, therefore, okay, our 95% confidence interval for this particular sampling, number 1, will be, okay, we subtract these, so we have 101.37 on the left side and 132.43 on the right side. And this is now our final answer, the confidence interval for our mean. So therefore, if we try to draw this as a T distribution, okay, like this one, we have a T distribution. Our sample mean here in the center is 116.9. And then there is a confidence interval going to the left. And this one is 101.37. And then going to the right, we have 132.43. So that's our confidence interval, specifically 95% confidence interval. So now, because our different samplings here vary with their sample means and sample standard deviations, but all come from the same population, we can come up with a template like this. Okay? So take note, in this template, we left out the sample mean and the standard deviations, but we had a constant here already, okay, based on a 95% confidence interval. So you can simply replace the mean here with whatever sampling you choose. Say you choose sampling number 2, you replace the mean here with 132.8, and then you replace the S, the standard deviations here, with 32.62. And say if you choose sampling number 5, you replace the means with 111.9 and the standard deviations with 20.46. And you'll end up with this notation. So as what you might have already imagined, we will end up with varied confidence intervals for the different samplings. So remember, there are 5 samplings, 1, 2, 3, 4, 5. We also end up here with 1, 2, 3, 4, 5 confidence intervals. Okay? They might be different, but all of these confidence intervals of the mean at some point include the population mean, indicated here by this broken line in the center. Okay, so all of them include this population mean. In fact, because we computed for a 95% confidence for our class interval of the mean, or confidence interval of the mean, then if we were to make 100 of these confidence intervals, if we have 100 of these instead of 5, because we followed the 95% confidence interval, out of the 100, 5 of them will not include this sample mean. Okay? So 5 of them will not include the sample mean, and 95 of them, because it's a 95% CI, will include the sample mean. So far, the 5 samples that we have here, all 5 included the sample mean, or the population mean. Okay? So, what determines the length of your confidence interval? Okay? Here are some of the factors that affect the length of the confidence interval. First will be your number of samples. Okay? As your sample size becomes bigger, the length of your confidence interval decreases. What does that mean? It becomes more and more accurate. Okay? Because it becomes narrower. Now, what about on your standard deviation? As the standard deviation, which reflects the variability, increases, the length of your confidence interval also increases. So the greater the spread, the longer your confidence interval will be. So the lesser precise it will be. And what about for your alpha? Okay? So remember, our alpha, it can be 5% for a 95% confidence interval. As the confidence desired increases, so let's say we started from 95% confidence. What will be our alpha here? Our alpha will be 5% or 0.05. Okay? If we increase this confidence interval, if we make it 97% confidence interval, what will be our alpha? Our alpha will be reduced to simply 3%. So alpha decreases and the length of your confidence interval increases. Okay? So as you decrease alpha, your confidence interval increases. So here, the alpha will be perhaps this long, or the CI will be this long. But if your alpha is 3%, your CI can be a bit longer.